It's using gossip sub. So it has what they call the gossip domain, in which they are using gossip sub for block diffusion, for attestation, and for a few other things, which is a growing list. And these are a number of gossip subtopics. And then they have something which is called the request response domain, in which they are using libp2p protocols, request responses. And again, there are a number of protocols, like beacon blocks by range, which is, I think, used by the crawler, which was mentioned here before. So it's kind of complex stack. We will focus on the gossip sub part of it for now. If I can go to the next slide. Now? Okay. So zooming in a little bit on how gossip sub is being used. So gossip sub was designed like a generic protocol, but Ethereum is using it in specific ways. And these are just two examples how it's using it. So there are very different traffic patterns. When you are speaking of block diffusion, you have large messages, the blocks. It's a one-to-all, basically, traffic pattern. The block is sent from one to all. And these are kind of isolated instances. Every 12 seconds, a block is sent out, and then it has quite some time, actually 4 seconds to propagate. And then 8 seconds after, a new one will be sent. So you have this isolated sending of large messages. Then you have the attestation propagation, which is entirely different traffic patterns. So you have small messages, like 300 bytes, and many are sending to many in parallel. And you have lots of concurrent messages. And then there are a few other uses. So just be conscious that there are different. Let's zoom in to the block propagation. So when we are speaking of blocks, I said large messages, but what we are speaking of. And this is the block size grows in Ethereum, the daily averages since beginning. Then there was the merge, block size is kind of stabilizing, and then they started to grow, and then there was EIP 4844. So in between here, we were doing measurements. How is the block propagation using gossip sub in Ethereum? But what I was showing you before was a bit misleading, because those were daily averages. So daily average sizes is good to know, but that's not what the network has to handle. The network has to handle the individual messages. And this is the distribution of the individual message sizes. So this is the message size in megabytes. And this is actually an exponential, sorry, a logarithmic plot. And what you see here is that there are big blocks. There are blocks up more than 2 megabytes in size. So we were curious how this works. Actually, this was started as an exploration. The EF was artificially injecting large blocks into network. Then we figured out that there are actually already big blocks in the network. So we have these kind of organic big blocks. So we were looking into how these propagate. And we have a write-up on that if you want to go to the details. So these were the two setups. One was by the EF PandaOps team. They were setting up different nodes, 3 geographic locations, all the clients, multiple instances, and collecting data. And we were setting up our own. It's a home node, just connecting, running one client, but logging more, so we could then modify the code. So it was logging more and gathering some extra data. And then we analyzed. So what we get? So this is what you get on block diffusion as a function of block size. So if you take time, and there you should know that there are 12-second slots, and the blocks should diffuse in the first 4 seconds. And then you look at blocks of different sizes. So we have these buckets. So you take 100,000 blocks, and we put them into buckets, up to 32 kilobytes, up to 64 kilobytes, and then up to 2 megabytes. And then you are looking at how those messages arrive in time. Then you are getting these nice distributions of different messages, how much time they took to arrive. And well, the good news is that everything arrives in 4 seconds. Even the 2 megabyte blocks were arriving to these nodes in 4 seconds. And these are cloud deployed nodes, but it was kind of true for the home node as well. The bad news is that as you are increasing the block size, this curve is going to the right. So it kind of feels like increasing the block size more would create issues. Because then, if it would be like here, then only half of the nodes would be receiving the block in time, and that's not ideal for Ethereum. Okay? So, we did also other measurements, obviously. Since we had the data, we were digging into it. And we did like geographic location-based analysis. What's the delay in different countries, in different places in the world, in Sydney, in Amsterdam, in San Francisco. And well, what you would expect. There is some more delay. But it wasn't bad. The 4-second mark is still okay. Okay. So now we know that blocks can actually diffuse in the network, but we know that we want to scale more. So how do we scale? And that's where we have different options, right? From the networking perspective, we can change the slot time or change the 4 seconds to something. That's an option which is very controversial. So let's just eliminate that for a little bit. Small gains and controversial. Then there is gossip sub-improvements for large messages. And that's very interesting. It's just not my talk today. So let's just put that aside. And it's gaining, but relatively small gains compared to something which is sharding the data and doing data rarity sampling. So that's what I will speak about now. Data rarity sampling. Okay. So an intro into data rarity sampling. How many know what is data rarity sampling? Okay. Good. I will try to phrase it. Okay, so why we need data rarity sampling? And the answer is relatively clear. We have to do something if not all the nodes can get the block. Let's assume we have a block size large enough that not all the nodes can get the block in time. Then we need a solution in which not all the nodes are getting the block. Otherwise, the system is not working. Otherwise, we have a hard limit. So we have to figure out something. And what we can figure out is data rarity sampling. So, and then you have to dig into the details. So the first thing to realize is why nodes are downloading the data in a normal blockchain. And there are two reasons for that. They are executing it. So they need to execute it, and then they also need to know, which when they were executing it, it was not obvious, they need to know that the data was not withheld. Now there's data which doesn't need execution, but you still need the second knowledge, that the data is actually downloadable, it was not withheld. So if we can find data which is not executable, which is not executed, then we can handle it separately. And these are the so-called blobs. So blobs are just data which doesn't go into execution. It's not part of the execution layer. They don't care. It's just linked to the block. And then you have those blobs, extra data. And then we can handle those separately. So this is the notion of blob, very important. But the blobs are introduced in AIP 4844, which is not yet data rarity sharding, because these blobs are still going to the nodes. So yeah, this is not a nice plot. I hope someone has a stacked plot here for this. So I was just trying to put the blobs there. So what happens is, actually the block sizes were going down, but there are the blobs which should be sent to the nodes. And they are still getting it all if you don't have data rarity sampling. So we are sending more data currently to the nodes, just to, it's not part of the block, it's part of the blobs. Okay, so we have to figure out something, and this is data rarity sampling. So the basic concept is you go probabilistic. So you don't get all the data, you just check that the data is there with a probabilistic check. It's a statistical test. Let's say that's the blob data, you chop it up to 4 pieces, and then you're just checking one piece. And if you're checking the piece, you have your own view of whether the data was made available. This is what I call the DAS view. So you have your test. And the first case, it's passed. In the second case, you were testing 2 out of the 4, and your test is failing because you see that part of the data is not there, okay? And then what I call the God mode is if you look at it from outside, you know if the data was available or not, right? So in the first case, the data was available. In the second case, the data was not available. So your test is good. It's a 2 positive here. It's a 2 negative there. But then, you have problems. Because you can easily get into this situation. Your test is passing, but actually the data was not available. And that's a huge problem, because then the data was withheld. And that you want to avoid at all costs. Well, not at all, but you want it at very low probability that you are in this situation. And that's where you need something which makes this probability very low. And that's where something comes in, which is the erasure coding. So this is why we are erasure coding the data. Because after erasure coding the data, the test is changing. So you had a test in which you were looking at k segments, and your probability was kind of linear to catch that the data is missing. If you are doing an extension using erasure coding, then you have this nice probability that, let's say you are extending the data to double it, and then if the data was not available, so more than half of it was missing, only then you have to detect. But that's easy to detect, like that more than half of it was not. Because I'm just testing and it's already 1/2. And then I'm looking at another block and it's already 1/4. And maybe I'm getting 3 pieces and then it's already 1/8. And it's easy to, if you have lots of these pieces, then it's easy to get into a situation where my test is very safe in some sense. Okay? So this is almost what we are doing with sampling. We have this sampling amplification effect with using the erasure coding, in which I'm checking only a few pieces, but I'm getting very sure very fast. Okay, this is not all, which is database sampling, because you also have to prove that the data that I sampled is actually the data that had to be published. So you can easily be in the situation where there was the data, it was extended by erasure coding, and then I'm downloading that piece, and I managed to download it, right? Sounds good, the data is there. Unfortunately, what I downloaded is not the erasure coding extension of the data, so when I would like to actually use it, I would figure out that I was cheated. So to make sure that cannot happen, we have to prove every single piece that they actually belong to the erasure coding of the original data. So that's where KZG commitments come in. So when we are extending the data, we are committing to the data, and then we even have proofs for every single piece, so that just by downloading a single piece, you know that you downloaded actually, your test tested what you wanted to test, to put it simple. Okay. So now I hope you kind of understand what data ready sampling is. You extend the data, you sign the data, KZG proof the data, KZG commit to it, and then you sample it. Okay. Now this was easy. Now we have to do it over the network. And this is where we start to play. So we were already speaking about the data, the concept of blobs, the concept of encoding, and that we have to sample it over the network. The question is how you sample, from who you ask this piece. Where do you get it from? And that's where you should realize that you need actually a place to get it from, and it cannot be just the block producer. So you need to first disperse the data. So you first send out the data into the system, and this is what you call dispersal. And the role of this is to make the data available in the system. So this is the DEA part of DAS. And then you have the S part of DAS, which is the sampling part. So then you have to sample, and we call this this place custody. So you are sending out the data, there are nodes custodying the data, and then you are sample from this custody, and only then you are sure that the data was actually made available. Okay? So we have kind of two networking problems here. Sending out the data, and then sampling. Okay, so let's now be more concrete. How we encode the blobs. So until now I was having this toy example. This is the encoding that we would use in FullDAS when we are going for this 32 megabyte. So that's, you have 32 megabytes of data, that's the upper left corner. And then we are extending it basically 4 times. First, we are chopping it to a bunch of pieces, 256 by 256. So what's that? We have 64,000 pieces. And then we are extending it in 2 dimensions with a 2-dimensional Ethereum code. And now we have 250,000 pieces. And that's what we handle in the network. Okay? So there you can see the sizes. But the essence is you had 32 megabyte, you chop it to a bunch of pieces, you extend it to 4 times more pieces, and then you need networking which handles all this. What's the networking? First part of networking is sending the data to custody. So dispersal to custody. So you have each beacon node is taking a part of the data, and it's important, obviously you are not taking all, you are taking a part, and we are specifically focusing on rows and columns. So you are taking a few rows or a few columns, and then everyone has his own column allocation, and we have to make sure that this happens in a few seconds. So the problem is we have 1 million validators. We have only 5,000 nodes which are in the network. So it's not the validator count, but basically the node count which matters. But we have 8,000 nodes. We have these 250K segments. We have these 1,000 rows and columns, so 500 plus 500, and 4 seconds to make this dispersal happen. And then there is the second networking problem, if I can switch to that, which is the sampling. So now you don't have the block producer, you have a node. And that node is, we said, selects random pieces, and then downloads it from the custody nodes. And then if it manages to download all, then it's happy. It's a thumbs up. The DAS test was passing. So we actually randomly selecting 73 pieces. 73 because that's the giving us the minus it's giving us a very low probability that that the data was not available. Okay, so this is the sampling problem. And from the networking perspective, this is a very different problem, right? We just need these small samples, 40 kilobytes of data, but we need it from random places in the network, and we need it fast again. Okay, so I will focus on the dispersal problem and not on the sampling problem. Now we have things in the sampling as well, and I will focus on the FullDAS case. There is also PeerDAS, which is a version which is less aggressive, let's put it this way. But I don't think I have time to kind of focus on this one. Again, we have a write-up on this, where we kind of detail also the details of PeerDAS and FullDAS. Well, PeerDAS is a simpler version. It has just 1-dimensional encoding, and you only have columns, and you are sampling columns. While in FullDAS, and you have much less data. In FullDAS, you have this 32 megabytes of data encoded to 128 megabytes, and you are sampling at the cell level. So your sampling, as I said, is 40 kilobytes, not many columns. And we have a bunch of techniques that we developed to make this happen. I'm not saying we are there yet, but we are working on this. And today I would like to focus on the libp2p aspect of this, obviously. So let's see how to disperse to custody. And these are options here. So I will start with the first one, and I would stick with the first one mostly, which is if you can easily realize that there is a natural mapping between gossip sub, the idea of gossip sub as a pub sub, and the dispersal that I was showing. You have 500 columns, 500 rows. Those are like 1,000 gossip subtopics, right? And you could just use that. Then you can do other things. You can modify gossip sub to fit the use case better. Or maybe you can have a dedicated libp2p protocol, which you call maybe disperse, which is doing the whole stuff. Or maybe you can have a dedicated libp2p protocol, which is doing the whole thing, like the dispersal and the sampling at the same time. Or maybe, and I should mention this as well, maybe you are not using libp2p for one of these parts. Maybe you are doing the sampling over UDP, which is not yet well supported in libp2p, but you are doing the dispersal with gossip sub. And there are other variants there. Okay, so let's see what this means. So let's see we have a gossip sub mapping of the problem. You have this 500 topics plus 500 topics. And you have all these nice reliability mechanisms of gossip sub to make this happen. You have the mesh set up for all these 1,000 topics over the overlay. You have the I want exchanges over all these topics. Cool. And every message passing is going over reliable transport over TCP. Plus, we are adding 2 more layers of reliability, which you can actually implement on top of gossip sub, and that's what we did. So we don't, for this one, we are not changing gossip sub, but you can implement on top. One is you have the erasure coding, which you can use as a forward erasure coding. So whenever you are on the topic of a single row, if you have half of the row, you can extend it and you have the whole row. And you can use it in a smart way that you are sending the cells, and then once you have half of the cells, you can extend it and then you can feed that into the network. And you have this cross connection. So if I'm on a topic and I received a cell, and I happen to be also on the other topic of the column, so I received it in the row and I'm also on the column, then I can just bump the message from the row to the column. So we have this cross-topic message passing also, which we can still do on top of libp2p. And yeah, you can play with this. So it's much more reliability techniques than we need. It's 5. So you can play with configurations. Like you can set up your gossip sub to have a degree of only 4 because you have other techniques anyway to fight losses. And we paid a lot. But let me go to what you have beyond the simple mapping. So previously I was showing the simple mapping, but this is beyond the simple mapping. So we have these 250,000 cells that we want to send out. And actually we can decide how we are sending these out. We can send out entire half rows, or we can send out messages which are single cells, and that's our decision whether we want to handle it cell by cell or in larger chunks. We can send out things on rows, we can send out things on columns. The block producer has to send out lots of these. So what you have to realize here is that, for example, what's sent out first by the block producer would make things unbalanced. So if you just take a normal implementation and you are sending this out, then the first thing I'm sending out would go to all my neighbors. So I would feed it all over, and then the second one and the third one. So and by the time I would arrive to the last one, it would be a problem. But I don't have a difference between these cells. One is like the other. So I could do a technique in which we just make sure that one copy of every cell is getting out of the node which is pushing it. And only then I'm thinking of sending a second copy, seeding it to somewhere else in the gossip sub mesh overlay. So I'm not doing the usual thing of sending them all together, but making sure one copy of every single cell is sent out first, and then only then sending out a second copy. It's kind of like the latest first scheduling that you are using in BitTorrent. There is something called staggered sending, which is similar, but it's not handling like the notion of we know that there is this block and these cells are basically all together part of a single service. We have something which is kind of a batch partitioning, basically. So you just need the notion that these belong together so that you can handle them in this way. And that's something we are playing with. Another thing that you can play with as a modification to the base gossip sub is if you realize that the topic address space that I said 500 topics is not just strings, it's extremely structured. So you have this in FullDAS, it's 9 + 1 bit ID space. 9 bits for the column ID, and 1 bit for was it a column or was it a row. It's a 10-bit ID. And you can do a lot of things with the 10-bit ID. You can have short identifier, you can have bitmaps, you can have many things that just generally Gossip Sub doesn't have. Obviously, you can encode things, so you can save a lot on these, especially with the bitmaps. You can save a lot. Once you saved that bandwidth, you can piggyback messages, and you can just improve efficiency. This is something we are not doing yet. And things you might want to use, make sure you're using Quick, or maybe use UDP, and so on and so forth. So that brings me to the last section, and I don't know how I'm with time. So the last section is about simulation. So we have written a few simulators for this. Our first simulator is a Python simulator, which is not libp2p related in the sense that it's taking the idealistic view. So we don't have TCP slow start. We don't have these kind of issues which a network have. We just look at what if we could just send out messages fast and do everything fast, also the sampling fast, and we would not have the implementation related issues and some of the network protocol related issues. And then we wrote a second simulator, which is this NIM edition, which is actually taking the NIM the NIM libp2p implementation. So it's a simulator which is using something called the Shadow Network Simulator Framework. So the Shadow was developed for Tor, and I think there will be another talk maybe that is speaking of this. It was developed for Tor, and it has this very nice property that you are running real code. It is capturing the system calls, so you are firing up a bunch of processes, 1,000. These processes are running in a virtualized time, basically. The system calls are captured, and then they kind of stop and start based on how fast you can simulate. So you don't need a beefy machine. You need a beefy machine because you need lots of RAM. But you don't need a beefy machine in the sense of you have to keep up with time, because time is relative. And it handles that using the original code without modification. Then, obviously, there are the details. But to some extent, it works. As I said, we are using the NIM libp2p implementation, but we are modifying it a little bit to change how we are publishing things and turn off, turn on things. And then there is a small, stupid data with the sampling application logic on top, which is doing the things like taking the message out of the column and putting it in the row, or realizing that there was enough messages arrived in a row, and thus doing the erasure decoding, basically, and generating the other messages. Being a simulator, we are faking the erasure coding. There's no point in spending the CPU cycles on actually doing it, but it's something which is easy to fake with a read-storm code because you have just the mathematical properties so that you can fake it. Okay, so where are we with these simulations? The thing is running. What you see here is a example where the block size was configured as, so that's 8 megabytes, that's in bytes. And then you can configure the number of rows, the erasure coding on the number of rows, the number of columns, and this is not the sizes that I was speaking about. This is not the 32 megabyte. This is just 8 megabytes of data and only 256 plus 256 rows and columns. But it was running with 500 nodes, for example. So you can easily fire up a simulation. 500 nodes running is a single machine. 500 nodes running real implementation of libp2p. A node which is sending out 8 megabytes with all this complexity. 499 other nodes which are receiving parts of this. And then every 12 virtual seconds generating a new block, or blob actually, and then going with this in a loop. And you can define the uplink and downlink bandwidths of the nodes and a few other parameters. So this is the tool that we are playing with. It's derived from a tool which was done actually by the libp2p team, which might be presented actually today. So it's kind of a modification of that. We didn't write it from scratch. And there you have timing measurements. So here, it's a bit ugly, apologies for that. But what you see there is the block size. What you see here is the sample count. So actually, we are also doing the sampling, which I was not speaking of, but every node is then getting 71 pieces. And actually, here they are doing it over libp2p. And then there are nodes which are custodying 2 rows and columns, and there are nodes which are custodying 32 rows and columns. So we have this heterogeneity in the network. And then you have the diffusion time in milliseconds of everything that has to be diffused. And so this is the time, the latency of arrival to the nodes of everything they wanted to have with the custody. So this is the first block that we sent out. And on average, nodes received everything that they wanted to have in the dispersal, so the custody is full, in 620 milliseconds. And for other blocks, it was like, there's a variance there, obviously, because there's a bunch of randomization. And then we also have statistics on the spread of this, how much is falling in the first second, second, so we could also plot the distributions. And then there is also this, oops, I hope I didn't, yeah, okay. So there is also the sampling, how much time it took to get the data to custody, and then to sample from custody. So every node is sampling as well. Then this is the time it took, on average, to sample. And that's, again, a distribution, which has a much larger spread. That's something to think about and work on. But we are in a situation where we can use an existing libp2p implementation and kind of run this complexity. We've seen a bunch of inefficiencies, and we know that not all the libp2p stack, I mean, we are kind of using it a bit out of context. So obviously, implementations are not made for this. So we had to fix a few things. The simple things like when you are getting a message on a row and you want to bump it on the column, it already gets filtered, for example, in NIM implementation, because you already received it and you are supposed to send a message already to all the topics that it belongs to. So it's just, there are many of these details because this is complex and cumbersome, but this is where we are. There is hope. There are also other hopes. People are working on, we are also working on UDP-based solutions for the dissemination, UDP-based solutions for the sampling, other stacks, totally other solutions. So, yeah, thank you. Questions, I think, if there is time.
Sorry, this is all the way back to the start of your slides. Yeah. You showed a graph of the block propagation. Were they simulations or were they real?
No, those are main net.
And I think you had a statistic there that was like 80% came in 2 seconds.
These?
Yeah, these.
Yeah.
This is real mainnet.
This is real mainnet before.
Okay, cool.
So this is okay, yeah. So if you would like to plot this, you would have to measure in every single node, get the timestamp, and then you can plot a nice curve. Now, we cannot do that. We can only do the contrary. We are measuring in a single spot, and then we are getting lots of blocks, which were generated in many parts of the network. And then we are plotting that distribution. So this distribution is not that distribution. The two distributions are a bit different, if you think of it. We are not seeing how one block was sent to all the nodes, but we are seeing how one node was getting all the blocks. And the two are related, but not the same. But that's why we also run a home node, for example. Again, you have this asymmetry problem, this problem, but it gives you kind of confidence that the distributions are telling you something. Then what exactly they are telling, that's a nice detail to discuss. Yep. Yeah. We didn't check where it was published from. We are not supposed to check that, right? So this was randomly. There was also a detail here that different clients had different reporting ways, and therefore we had to look into different clients, and they had different statistics, not because they are receiving, not just because they are receiving with different, not just because they have different implementations and different design decisions, etc., but also because they are reporting the reception of the block differently. Maybe later. So that's why we also did the local test in which we modified the code. That was the NIM code. We know what happens inside, and then we are confident that we are measuring what we wanted to measure. Yep.
Thanks. That's maybe a bit off topic, but you mentioned that we want to avoid at all costs that some data is not available. I mean, why is that? Why do we care?
Yeah. You brought up the chain, basically. So it means many problems if you can withdraw a part of the data that the block is committing to, then you can mount a number of attacks. So blob data is typically layer 2 data, and that means that you can mount different attacks on the layer 2, which was supposed to use the layer 1 services. So the layer 2, if it's an optimistic rollup, then you can do one type of nested things. If it's a ZK rollup, then you can do another type of nested things, kill accounts, log them forever. You can do a bunch of things that is not nice. Any other questions? Thank you.